Let's say you're traveling on a train that is going very fast.
Your friend, Albert Einstein, stands on the platform next to the train. Neither of you are accelerating. You both travel at constant velocities. In other words, your perspectives represent inertial frames of reference, and the laws of physics apply equally.
You are bored in the train, so you shine a beam of light at a mirror.
As the beam bounces to the mirror and back, you measure the distance it travels to be half a meter. To you, it looks like Einstein and the platform are moving while you remain at rest, but to Einstein it's flipped. He and the platform are at rest while you're moving.
So, when he sees you shine the beam of light,
it looks like it's traveling a greater distance because he sees the train move in the meantime.
We know that the speed of light is constant no matter what.
Light always travels at nearly 3 times 10 to the 8 meters per second. So if speed is constant and distance increases, time must slow down. This is called time dilation, as described in Einstein's special theory of relativity.
For objects traveling at incredibly high speeds, almost the speed of light, time slows down relative to an outside frame of reference, so that the speed of light remains constant no matter which inertial frame of reference you are looking at it from.
We can calculate just how much slower time moves using the Lorentz factor. Relative to a stationary frame of reference, time moves slower in a moving frame of reference by a factor of 1 over the square root of 1 minus the velocity of the moving reference squared over the speed of light squared. This is called the Lorentz factor. If we look at our example, if Einstein calculates the time it takes for light to bounce to the mirror and back to be t, then relative to Einstein, the time it takes in your reference frame is gamma times t. Einstein perceives that time is slower for you because to Einstein he is stationary and you're moving, but to you, you are the one at rest. Thus, time is relative.
But it's not just time. When we take into account various frames of reference, length starts to act funny too. In fact, from Einstein's perspective, the length of the train will appear to contract.
Let's examine this concept in further detail. We know that the velocity of the train is constant, and that relative to Einstein, time is shorter. So the distance the train passes in a given frame relative to Einstein, its length decreases. This is length contraction, when the length contracts in the direction of a moving frame of reference relative to a stationary frame of reference. At everyday speeds, time dilation and length contraction are extremely small, but for satellites and rockets, the effects are significant.
This all just shows us that even in physics, the reality that we perceive might not be the same as everyone else's. It's all a matter of perspective, or in other words, our inertial frame of reference.